spring hangs vertically with a rest length of 8 centimeters. A mass of 2 kilograms is hung from this spring, and when the system reaches equilibrium, the spring is stretched to a length of 12 centimeters. What is the spring constant of this spring? If the mass is pulled down such that the spring is stretched to a length of 14 centimeters before it is released, what is the period of its motion? If another identical spring is attached to the end of the first, and the same mass is reattached to the end, how does the spring constant change? How does the period change? If the two identical springs are now hung side by side and the same mass is reattached to the end, how does the spring constant change and how does the period change? The three situations that we are dealing with are the original spring, two springs in series, and two springs in parallel. Our known quantities are L rest, 0.08 meters, L naught, 0.12 meters, L stretched, 0.14 meters, and the mass, which is 2.0 kilograms. Our unknown quantities are the spring constant of the original spring, the period of the original spring, the spring constant of the two springs in series, and the period of the two springs in series, the spring constant of the two springs in parallel, and the period of the two springs in parallel. We will begin by finding the spring constant of the original spring, K naught. We will start with the momentum principle. In this case, our motion is in one direction, and thus we can simplify from vector to scalar quantities. Additionally, the momentum change with respect to time of this system is 0, so we can simplify to the net force in one direction equals 0. For this problem, we will define up as being positive and down as being negative. Thus, our net force is given by the negative force of gravity plus the positive spring force. This is equal to negative mg plus K naught times L naught minus L rest. This may seem to contradict how Hooke's law is given. However, we can tell from our qualitative reasoning that the force must act in the upwards direction and thus is positive here. We can then solve for K naught by bringing mg over to the other side, then dividing by the quantity L naught minus L rest. We can do a quick unit check here to make sure that we are correct before we move on. Our answer has units of kilograms times meters per second squared all over meters. This simplifies to newtons per meter, which are the units we expect for our spring constant. Plugging in our values now to solve for K naught gives us an answer of 490 newtons per meter. We will now find T naught, the period of the original spring mass system. We know that the oscillations of a spring mass system have a frequency given by square root of K over M. The period, in turn, is given by 2 pi over this frequency omega. Plugging in, we then have that the period is given by 2 pi times the square root of M over K, which in our case gives us an answer of 0.40 seconds. We will now do a quick unit check again before we move on. Our symbolic answer has units of kilograms over kilograms times meters over second squared times meters. The kilograms and the meters both cancel, leaving us with 1 over second squared inside the square root, which gives us a final units of seconds as we desire. We will now move on to finding the spring constant and period for the system of two springs in series. We can solve this problem more easily by using ratios rather than solving for the quantities explicitly. This also saves us from doing additional unit checks, as all our answers will be determined in terms of the previous answers, which we already have checked the units of. We know that the effective spring constant of springs in series is given by the relation 1 over K effective equals 1 over K1 plus 1 over K2. In our case, the springs are identical, and this relation becomes 1 over K plus 1 over K, which equals 2 over K. This then tells us that the effective spring constant is 1/2 the original spring constant. Thus, K sub S is 245 newtons per meter. We will now find the ratio of Ts over T naught. We know that the period of the springs in series is given by 2 pi times the square root of the effective mass over the effective spring constant. Now, this can be simplified by canceling the 2 pi and bringing all quantities under the same square root. Additionally, the mass effective here is just the same as the original mass, and thus these masses cancel, leaving us with the ratio of the periods equal to the square root of K over K effective. We can now plug in our previous answer, which related the original spring constant to the effective spring constant of the springs in series. We now have square root of K over 1/2 K, or that the ratio of the period of the springs in series to the original spring system is square root of 2. This tells us that the period of the springs in series is 1.41 times longer than that of the original spring system. We will now solve for Kp and Tp using similar methodology. The effective spring constant for two springs in parallel is given by K effective equals K1 plus K2. In this case, since the springs are once again identical, this simplifies to 2K. Thus, Kp is 980 newtons per meter. We will now solve for the ratio of Tp to T naught. Similarly to the above problem, this is given by the square root of K over K effective. In this case, this becomes the square root of 1/2. This tells us that Tp is given by 0.707 times T naught. Once again, we do not have to perform unit checks on these answers, as ratios are inherently dimensionless.